All right. No. Share. And we need the notes. Yep, and we're going backwards. That's okay. Let's get rid of this so we get to do all this. All right, here we go. Students will be able to decide where functions do not have a derivative. 3.2 after the video. In exercise 1 through 4, compare the right hand and left hand derivatives to show that the function is not differentiable at the point. Find all points where f is not differentiable. So we have the left side. Oh, look at that. Okay. That's kind of fun. Yeah. Boing. Yeah, you can bounce it. Boing. The Pong. All right, so got to work. Limit, let's see, we're approaching 1. So limit as h approaches 0 of f of 1 plus h minus f of 1 over h. So we have the limit h approaches 0 of h over h, which is the limit as h approaches 0 of 1, which is 1. So that's the left-hand limit, or left-hand derivative. And then we have the limit as h approaches 0 of 1 over 1 plus h minus 1 over 1 over h. Because the right-hand function is 1 over x. So we have the limit as h approaches 0 of, I'm going to multiply all of this by 1 plus h to get rid of the complex fraction. So 1 minus 1 plus h over 1 plus h times h. We have the limit as h approaches 0 of negative h over h times 1 plus h. Those cancel. So we have the limit as h approaches 0 of negative 1 over 1 plus h. And that's negative 1 over 1, negative 1. So the slopes are different. The left-hand slope is not the same as the right-hand slope. So there is no tangent line at that point. But if I said, draw a line through that point that only touches the point one time, the problem is, because that's what a tangent line is, right? You could draw lots of those. So that's a big issue with saying that, there's a tangent line there. There isn't one. I guess because, well, first of all, the two tangent lines aren't the same, but you could draw a whole bunch of them that would touch that point in one place. So that's not a tangent line. So a couple ways to look at that. The graph of a function over a closed interval, D is given. At what domain points does the function appear to be differentiable? So where is this differentiable? From -2 to 3. I don't see any place where there's a corner or cusp or discontinuity. B, continuous but not differentiable. None. Continuous but not differentiable is a cusp or a corner. It's still continuous there, but not differentiable. And we saw that on the last one, right here, where we had this cusp / corner hybrid place. There is a point there. That function is continuous, but it's not differentiable. We don't have that on number 6. We don't have cusps or corners. C, neither continuous nor differentiable. That means there's some sort of discontinuity there. It's not continuous and therefore not differentiable. None for this one. This is a nice smooth curve, continuous everywhere, pretty much differentiable. Well, differentiable everywhere. Here's a more interesting one. Letter A, where is this differentiable? Well, from -2 to -1, not including -1, there's a corner there. Then -1 to 0, there's a discontinuity there. 0 to 2, not there because there's a removable discontinuity. And then 2 to 3, and differentiable at 3 because it's an endpoint and it's a solid dot. Any questions on that? So I had to skip the corner, skip the jump discontinuity, skip the removable discontinuity. That's where this is differentiable. B, continuous but not differentiable. There's only one spot right there. So at x equals -1. That's the only place where that's happening. Continuous but not differentiable is a cusp or a corner. C, neither continuous nor differentiable. There's your discontinuities. So at x equals 0 and x equals 2. It's not continuous. And if it's not continuous, it's automatically not differentiable there. Any questions on those problems? The function fails to be differentiable at x equals 0. Tell whether the problem is a corner, a cusp, a vertical tangent, or a discontinuity. All right, so we're going to use calculators for that. Close. Y equals x to the 4/5. What do you think's there at 0? It's very subtle. It's a cusp. It is curving very slightly. So that is a cusp there. Find all values of x for which the function is differentiable. All right, number 32. Third root, that's in math. I think number 4 is third root. 3x minus 6 and plus 5. Let's graph it. There is a vertical, I think there's a vertical tangent or line right at 2, 5. So, and I find all the values of x for the function differentiable. -infinity to 2, union with 2 to infinity. So vertical tangent lines means it's not differentiable there. If we have a vertical tangent line, then when we take the derivative of this, what's happening? I know it's a very vague question, but why would we have a vertical tangent line there? What's happening when we take the derivative? Say it loud. What's that? Slope of the tangent line is undefined, so when we take the derivative, what does that mean? How do you get undefined? Yeah, we have 0 would be in the denominator. So that's why if we get those vertical tangent lines, we say it's not differentiable there. All right. We'll learn them. We'll find out how to take that derivative, but we're not quite ready for that yet. 3, cosine of math num absolute value of x. If you're in physics and you've used calculators already, you're probably in degrees, maybe. We do everything in here in radians. So make sure your calculator is in radians when you're going to use a trig function in here. All right, graph. Looks fine, right? But it's not. It's not fine. If you look very closely at this, right here, you notice it's a little different than all the others. It comes to a point. I don't know if this will help or not. Nope, that made it worse. It made it look much smoother. But on a zoomed out version is probably better because you can see how this is nice and rounded at the top, and this one quite is not. So there's a cusp there at 0. So negative infinity to 0, 0 to infinity. The problem was at 0 there. There's a cusp there. Oh, is that it? That's it. Well, that's quick notes. We didn't miss much, did we? By me skipping ahead. All right. Yeah. Let's stop this for a second.